In today's notes, we're going to look at how to use the sum and difference identities. So before we start actually using those identities, let's just ask a question at the top. Is this statement true? Is sine of 45 degrees plus 30 degrees equal to sine of 45 degrees plus sine of 30 degrees? It may seem like a simple yes or no, but let's just double check it. Especially since I have sine of 45 plus 30, let's go ahead and use our calculator. It's very rare that I have you guys use it, but let's use it to see if this statement is in fact true. So I'm going to go ahead and pull my calculator onto the screen. I want you to keep in mind that you have degree currently for the 45 and for 30 degrees. So when I use my calculator, I want you guys to make sure that you put this into degree mode. So we're going to go into a new document, and I'm going to go ahead and add a calculator. Luckily, I see here that this is already in degree mode. If this is not currently in degree mode, you need to put this in degree mode, because if you're trying to calculate based on what you have on your paper, this won't work if you don't have it in degree mode. Okay, so let's start plugging things in. I'm going to plug in the left-hand side of the equation, which is sine of 45 degrees plus plus 30 degrees. Not sine, just 30. Okay, let me add both of those. You guys can go ahead and write that number down on your paper. And then I'm also going to take sine of 45 degrees plus sine of 30 degrees, which is the right-hand side of the equation. I want to see if both of these numbers, both of the computations, will be the same. Well, that sucks. These aren't the same. So let me go ahead and move this out of the way and let me copy down the numbers that we just found. So we have 0.9659, and then we also have 1.20711. Okay, well, that's not fun. I thought there was going to be both of them that were going to hopefully be the same. Well, both of these are not the same. Since these are not the same, this is not, of course, a true statement, which means we can't use this as a sum identity. So I'm going to put down here, this is not true. Okay, well, we need to think, what equation can I use that will give me a sum identity that will be true? I'm so glad you asked that. This chart here is going to help you with that. You guys already know what I'm probably going to say, probably. I don't like to have you guys memorize things for no reason. This you need to memorize. Especially with the signs, it's extremely important that you guys pay close attention when you're doing flashcards or when you're committing this to memory using whatever resources you're going to do, that you keep in mind what sign you're going to have. So for instance, if you notice here for the first equation, we have sine alpha, this is alpha, and beta, which is here. So let's say you're going to add both of these, sine alpha plus sine beta. Well, what you would use is you're going to do sine alpha cosine beta plus, you're going to use that sign on the top because this is the top sign here. You're going to use the top sign over here. Plus sine beta cosine alpha. And that would be the same for the bottom sign. So let's say you did sine alpha minus beta. Well, if you did that, you would do sine alpha cosine beta. And keep in mind, guys, in between these, you're multiplying, so that's multiplication, minus sine beta cosine alpha. It might seem, oh, Ms. Tapia, that's super easy. I don't need to remember that. No, you do, because when you get to cosine, guys, it's going to flip. You're going to have cosine alpha, we'll say plus beta, cosine alpha times cosine beta minus top sign. You're going to use the top sign here. And then, of course, on the right-hand side, you're going to continue sine alpha times sine beta. So, guys, it seems pretty simple with, oh, I just need to memorize that whole chart. Make sure you know which signs go where. Okay, so before we actually start doing examples 1, 2, and 3 below, I need you guys, and I know you love doing this, in whatever space you can find, I want you to create your unit circle chart. Yes, we're coming back to this unit circle chart, so let's go ahead and fill this in. We're going to go ahead and create our unit circle chart that we've been using for a while now. So we have our unit circle chart. If you're still not done, pause the video. You can definitely finish it up and then unpause it. But I have all of my chart filled in. The reason why I'm doing this is because as I start using my formulas at the bottom of the page, we're going to need to actually compute the sine of certain degrees or radians, and same thing for cosine and tangent. So if you have this chart readily available, you won't have to worry about, hey, what's sine of pi over 6 again? You already have it here. So we're going to go ahead and look at example number 1. So with example number 1, this asks you to identify the sum or difference of sine of 105. Okay, well, it doesn't still tell you specifically if you need to use the adding or the subtraction. So it doesn't tell you to use sum or difference. So you get to pick. Okay, well, let's think about this, because I definitely made, let me zoom out for just a second, I definitely made my unit circle chart. If I can use that as much as possible, it would be great. So let's go ahead and look at 105. Okay, let me think about this. 105, I could rewrite this, I guess you can write this down. This would technically be sine of 150 minus 45. If you actually compute that, 150 minus 45, that'll give you 105. But why did I probably say, well, you don't really have to write this down? Well, if you look at this, sure, 45 degrees is on the unit circle, on that little chart that I have right up here, but is 150. Keep in mind, even though all of this is in the first quadrant, I don't know off the top of my head what 150 is. So if you can possibly do this, write these in terms of these top angle measures that we already have, because it'll be easier for you to compute. So unfortunately, 150 and 45 isn't directly on that chart, and I'm trying to use something that's actually on that chart. So think about it, guys. What numbers can we add or subtract together that will actually be on my unit circle chart at the top? Well, there are two numbers you can use. We could use sine of 60 degrees plus 45 degrees. Okay, well, it does require you to understand up here at the top which angle measures represent 60 and 45. 0 radians is the same as 0 degrees. Pi over 6 is the same as 30 degrees. Pi over 4 is 45. Pi over 3 is 60. And pi over 2 is 90 degrees. So if you have these all written out, it might be helpful for you to actually find some of those values that you're looking for. So let me zoom back out, and I'm going to try not to make you guys dizzy with how many times I zoom in and out. But for pi over 6, for sine of 60 plus 45, I need to figure out, based on this equation, what signs I'm going to use. Well, let me first label this. Your alpha and beta are already here. This is your alpha, this is your beta. So when you plug in these values, make sure that you plug them in as they're supposed to be. So since we're adding, I'm going to use my top sign. Since we're adding this guy here, we're going to use the top sign here. So let me recopy what we have. We're going to have sine of alpha plus beta equals sine alpha, let me actually make an alpha, cosine beta, sine beta, cosine alpha. I rewrote all of this so I didn't have to keep zooming in and out. So down here, we're going to make this sine of alpha, which we said was 60 degrees, cosine of beta, which is 45 degrees. Sine of beta again is 45 degrees. Cosine of alpha is 60 degrees. Well, you guys have the unit circle chart at the top. Let's go ahead and find those values. So I'm first going to identify sine of 60 and cosine of 45. So let me scroll back up. Sine of 60 is square root 3 over 2. Cosine of 45 is square root 2 over 2. So we're going to take those two numbers and we're going to substitute them in using parentheses. So square root 3 over 2, square root 2 over 2. Plus, because the sign on top said for us to use positive, we're going to do sine of 45 and cosine of 60. Okay, so let me look back at my chart. Sine 45, square root 2 over 2. Cosine of 60 is going to be 1/2. So down here, let me go ahead and plug those in. We're going to have square root 2 over 2 times 1/2. Obviously, that's the only pre-cal part. The rest of this is just algebra 1. So we're going to go ahead and combine. So we're going to multiply both of these fractions straight across. So we're going to make that first fraction, back to rules of radicals. When you multiply two radicals, you're going to actually multiply the radicands, which are the numbers underneath. So we're going to have the square root of 6 over 4 plus square root of 2 times 1. It's not going to change anything under your radical. It's not going to affect your radicand. So it's just going to be 2 over 4, square root of 2 over 4. Well, since both of these denominators are the same, I could do one last thing. I could rewrite this as square root of 6 plus square root of 2 over 4. My question to you is, can I combine both of these to make it the square root of 8 over 4? Unfortunately, you cannot. If you think back to rules of radicals, you have to leave the radicands the exact same. Square root of 6 and square root of 2 cannot be changed to where you can combine them. If you could simplify this radical to get it to reduce to a square root 2, then yes, you could definitely do it. But since it cannot be combined, this would be your answer. And that's it, guys. This is pretty much it. This is what we need. So as long as you can memorize the formulas in your blue chart correctly, you should be good with getting your answers. So let's go ahead and look at example 2. Okay, example 2 is cosine of 255 degrees. If you think back to what I said on the very first example, I suggested that you should try to use a combination of the angle measures that are in your unit circle chart. That's how we added on the last question, 60 and 45 degrees. You add both of them, you get 105. The issue is, cosine of 255, I don't think there's a way that I could add the numbers in my unit circle chart to give me 255 degrees. Okay, so we have to think and be a little creative here. If we can't use numbers that are in your unit circle chart, which again, reference the first quadrant in your unit circle, we're going to need to use numbers that are outside of that first quadrant. What I would suggest doing though, instead of adding or subtracting two numbers, so for instance, adding 254 plus 1 degree, instead of doing something like that, what I would suggest doing is finding two angles that'll add or subtract to 255, but will have reference angles in the first quadrant. Here's what I mean. So cosine of 255, there's plenty of ways we can get cosine of 255. Let's use cosine of 300 degrees minus 45 degrees. 300 degrees is in quadrant 4. Let me zoom out a bit. 300 degrees is in quadrant 4. Here's 180. Here's 0. Here's 270 to make sure that you understand that I didn't just make that up. 360 is here. And the reason why I'm using 300 degrees is because 300 degrees is exactly 60 degrees away from my x-axis over here where 360 is. So that means if I find my reference angle in quadrant 1, this would just be a positive 60 degrees. That would be my reference angle, and it would be the same distance as negative 60 degrees. If I go negative 60 degrees down, I'll get to 300, which is the same as negative 60. The good thing about knowing that is that if you're able to use the reference angle, which is 60 degrees, you could plug it into your formula. The only thing that you need to make sure you remember, and this is key, guys, so write this down. I'm writing it in red for a reason. In quadrant 4, what sign is cosine? If you think of all students take calculus, cosine is positive. That means that when you plug in your values for cosine of 300 degrees, which is what we're eventually going to have to do, and even sine of 300 degrees, you want to make sure that you include cosine specifically as a positive. So let's go ahead and look at our formula. Since I'm subtracting, I'm going to use the cosine formula here, but since I'm subtracting both of the numbers, I need to add the numbers when I actually plug in the formula. So underneath here, let me go ahead and plug in my formula. And guys, if you need space, be careful because I'm probably going to run out of space. We're going to use, this is alpha, this is beta. We're going to use cosine of alpha minus beta equals cosine alpha, cosine beta, plus, remember, we're going to switch that sign, sine alpha, sine beta. Let's go ahead and plug in our numbers. Cosine of 300 degrees, cosine of 45 degrees, plus sine of 300 degrees, sine of, please tell me I have space. Oh, I don't. Sine of 45 degrees. I tried, guys. I tried to fit it in. So now we just need to look at our unit circle chart again. Okay, well, we just said cosine of 300 degrees has a reference angle of 60 degrees because it's literally just 60 degrees away. If I look back in quadrant 1, cosine of 300 degrees is going to be the same answer as cosine of 60 degrees, and it's going to be positive. So let me look at my unit circle chart. Cosine of 60 degrees, cosine of 60 is 1 over 2. So in this first spot, I'm going to plug in 1 over 2. Positive 1 over 2. Cosine of 45, hopefully we already know, is square root 2 over 2. Let's look at sine this time. Okay, well, this is going to be a little different. Since sine is going to be in quadrant 4 for 300 degrees, sine is now negative. So keep in mind, sine is negative. So when you plug in that sine of 300 degrees, make sure you include a negative symbol. So let me go back to my unit circle chart. We're going to do sine of 60 degrees, which is going to give me square root 3 over 2. And then, of course, sine of 45 degrees is just square root 2 over 2. So down here, I'm going to go ahead and plug that in. We're going to have negative, because it's in quadrant 3, quadrant 4, square root 3 over 2. And then 45, sine of 45 degrees is just square root 2 over 2. From here, guys, that was the only pre-cal part. Algebra 1 is what remains. We're going to multiply straight across. And then we're just going to combine. Oops, let me actually write this underneath. So we're going to rewrite this as, okay, well, we're going to subtract both of these. And remember, we talked about this before. Since the radicand, which are the numbers underneath your radical, since both of those numbers are not the same, you cannot combine them into the square root of 4. We're going to rewrite this as square root 2 minus square root 6 over 4. This should be your answer. Let's go ahead, let me zoom out a little bit more. Let's go ahead and look at example 3 at the bottom portion of my page. Okay, 11 pi over 12. Okay, this will be a little fun because now we have radians. Okay, let me zoom in a bit for my tangent. Let's think. I need to find some numbers that will add up to 11 pi over 12. And especially since I have that 11 pi over 12, this is actually kind of nice. If you think back to your knowledge of Algebra 1, if you have the same denominator and you're adding or subtracting two fractions, you'll be able to just combine the numerators. So let's go ahead and make this tangent of, I'm going to add or subtract two numbers. I'm going to keep my denominators as 12, and I'm purposely going to put a pi in the numerator so I don't forget about it, because ultimately you want to have a pi in that numerator. Okay, well, let's think. I need two numbers that will add or subtract up to 11 pi over 12. I'm going to do adding. Let's do 9 pi over 12 plus 2 pi over 12. This will be my alpha. This will be my beta. All right, well, let's see what happens. Okay, so let me see. If I was to simplify this, this will turn into tangent of 9 over 12 will reduce to 3 pi over 12, or not 12, excuse me, 4, plus 2 over 12 will reduce to pi over 6. Pi over 6, 100% is in my unit circle chart. 3 pi over 4 is not quite in my unit circle chart. However, with this having a reference angle, I'll know exactly where to find it. So I'm just going to do this over here, even though you probably already know where it is. Here's 0. Here's 4 pi over 4. We're now in radians. 3 pi over 4 is going to be right here. There's a reason why I drew this out. In this quadrant, if you keep in mind that all students take calculus, we're going to need to use the tangent formula for this. Okay, let me just take a quick second and look at my tangent formula. Guys, do you see a sine or a cosine anywhere in this equation? No, you just have tangents. With those tangents, I'm about to recopy my formula below, but when you have all of these tangents, that means that you're going to need to keep in mind what symbol, positive or negative, tangent's going to be in this second quadrant. In quadrant 2, tangent is negative. So everywhere you start plugging in those tangents, you need to plug it in as a negative number. Okay, so let's go ahead and look back. I said that we were going to add both of those. So over here to the side, let me write out my tangent formula. So tangent of alpha plus beta is going to equal, I'm going to put it below. We're going to make this, actually, let me put it next to it. We'll do tangent alpha plus tangent beta all over 1 minus tangent alpha, tangent beta. And remember, when the numbers or the trig functions are stuck together like this, they're being multiplied. All right, so right now I want you guys to pause the video and I want you to see if you can finish this up. What would your answer look like? So again, just a friendly reminder, this is alpha, this is beta. I'm going to go ahead and plug this in. So in the formula, I'm going to do it in orange. We're going to have tangent of alpha, which is 3 pi over 4, plus tangent of beta, which is pi over 6, all over 1 minus tangent of alpha tangent of beta. Oops, that's pi over 6, not pi over 4. All right, let's go ahead and plug in our numbers. So at tangent of 3 pi over 4, keep in mind that your reference angle is going to show up in quadrant 1, which is pi over 4. Hopefully that was obvious for you. That's your reference angle to get from here to here. It's pi over 4 units. So at pi over 4 for tangent, let me look back at my unit circle chart. Tangent pi over 4 is going to give you a 1. But since this is in quadrant 2, you are going to give me tangent as a negative. So let me start plugging this in. This is going to give me a negative 1 plus tangent of pi over 6. I'm not going to keep zooming in and out. I'm just going to tell you tangent of pi over 6 is square root 3 over 3 divided by 1 minus tangent of 3 pi over 4. Let me actually plug in the correct number, which is negative 1. And then tangent of pi over 6 again is the same, square root 3 over 3. Keep in mind, guys, your tangent, especially for pi over 6, I didn't mention this before, but hopefully you guys remember, pi over 6 is in quadrant 1. In quadrant 1, all of your trig functions are positive, which is why I'm not putting a negative with this number. Guys, that was the pre-cal part. The rest of this is just algebra 1. So let me zoom out for a second and analyze how much space I have. Okay, I have enough space. We're going to have to simplify this. So let me go ahead and kind of get rid of the parentheses. Let's clean this up a bit. This will be negative 1 plus the square root of 3 over 3 divided by, you see, we're going to multiply that to give me negative square root 3 over 3, which means I'm technically going to have to add both of those. Goodness, ran out of space towards the bottom. So yeah, so we have the plus square root 3 over 3 in the denominator. So 1 plus square root 3 over 3. And we still need to simplify, guys. That's not an acceptable answer for me. So let's think about this. That's why I kind of analyzed my space. If I wanted to simplify this, what would I need to do? Okay, well, the first thing I definitely want to do, I got to get rid of these fractions. These fractions are freaking me out. So let me go ahead and multiply this whole numerator by 3 and this whole denominator also by 3. What that's going to do is it's going to eliminate that ugly fraction that I have and make it something a little nicer. So we're going to rewrite this as, I'm going to distribute that here, negative 3 plus just the square root of 3, because by multiplying these two numbers, the 3's are going to cancel. And then in the denominator, we're going to distribute this 3, and we're going to make this 3 plus the square root of 3. Okay, this in blue is so much nicer to look at. I still need to simplify it, though. What can I do? We talked about this before, guys. We can use a conjugate. So the conjugate for this is going to look like 3 minus the square root of 3, 3 minus the square root of 3. The reason why I'm doing this is because on your test quizzes and notes, it'll usually ask you to write your answer as a simplified fraction, which means that you cannot have this radical in your denominator. So we're going to go ahead and simplify this. By having both of these binomials, guys, you're going to have to FOIL the numerator and denominator. So right now, I want you to pause the video and see if you can rationalize this without me. All right, I started it out by FOILing. In the denominator, hopefully you notice both of the items in the middle, the radicals are both going to cancel, hence by me multiplying by the conjugate. And that's going to simplify further. The numerator is going to, you are going to combine both of these numbers and these. You're going to combine both of those. So you're going to get negative 9 minus 3 is negative 12. 3 plus 3, so when you're combining these guys, only combine the coefficients. Leave the radicands alone. They act as a variable. So plus 6 square root 3 all over 9 minus 3, which is 6. You're not done. You can still do really 1.5 more things. If you look in the numerator, especially since I see this 6, I know I can try to cancel. But before you just start canceling all random things, let's go ahead and actually factor out a common multiple. So I'm going to go ahead and factor out my greatest common factor here, which will just be a 6. And we're going to leave this as negative 2 plus the square root of 3 over 6. The reason why I didn't factor out a negative is because I see that the 6 in the denominator is positive. You can factor out a negative 6, but you're just going to have to distribute that negative again later. By factoring out that 6, I can officially cancel both of these 6's because you're multiplying this 6 by this whole parentheses. That's going to leave your final answer as such. Let me write my answer over here. we're going to have negative 2 plus the square root of 3. This would be your final answer. Guys, the hard part of this is not the pre-cal. The hardest part for a lot of my students is just the basic algebra 1 that's in this screen. Make sure you know how to combine like terms and how to not to forget to actually distribute as well. Because remember, for this one we had to FOIL, this one we also had to FOIL. So let's go ahead and look on the last page of this, so the next page, and let's talk about a few questions. Example 4 says, write the expression as sine, cosine, tangent of an angle. Okay, so we need to first figure out what is this? Well, I actually kind of saw this before, guys. If you look back on the first page, so look on this first page with me, this kind of looks the same. So let's start here. First thing I notice is that the equation you guys are looking at, example 4, it's definitely not tangent. Definitely not. There's not a single tan anywhere in there. So I'm going to go ahead and with my pen, I'm just going to cross out tangent. That's gone. Okay, this is either a sine or a cosine. Okay, the subtraction isn't really helpful. Let me look back at my equations. Sine has a combination of sine and cosine on both sides of your equation. Cosine has cosines all together and then sines all together. Okay, well, let me look back. This has a combination of both. So this equation is representative of some sine, either sum or difference formula. Just don't know which one it is yet. The good thing is, since we know that it's being subtracted, we know that if we look on the first page, if it's being subtracted, that means your original sign has to also be subtraction. So on the back side of this page, I'm pretty much using the sine formula here, specifically using subtraction. So let me go ahead and rewrite this on the other side. So I'm going to recopy my sine of two angles that are being subtracted. It specifically asked for you to write the expression of sine. This is what it's looking for. What was the original problem they gave you before you rewrote it as this? Okay, well, now we need to figure out the last thing. What's your alpha? What's your beta? Okay, well, in this case, your alpha should be whatever is first, and your beta should be whatever is second. So let me actually rewrite this before I write my answer. This is in the same form because this will help you with identifying your sine, alpha, and beta. Let's do sine, alpha, cosine, beta. And if you look back on the formula for the first page, this is the same formula. Cosine alpha, sine beta. Perfect. This is exactly what I wanted. Technically, the sine and cosine on this last part are switched, but they're still being multiplied, which allows this to work. So all I'm going to do here is I'm just going to rewrite like I had before. Sine of some number minus minus another number. So your alpha is going to be 42. Your beta is 17. These are both degrees. All we're going to do here is just subtract. 42 minus 17 is just 25 degrees. This would be your answer. Example 5. Okay, again, it's asking me to find sine of x minus y. So this is a difference quotient or difference identity for sine. Okay, it's giving me two things though. Cosine of x is 3 over 5, and it tells you where pi over 2 is less than x, which is less than pi. It also tells you tangent of y is equal to 8 over 15. Yes, guys, I know both of those are negative. This one's negative, this one's negative. I didn't forget. Where 3 pi over 2 is less than y, which is less than 2 pi. This is asking you to actually find what your sine of x minus sine of y is going to be. So let's go ahead and graph this out. The reason why I'm saying graph is because it's specifically telling me it's going to be in certain quadrants. Let's start with x. For cosine of x, it specifically says that you have 3 over 5, and that 3 over 5 is going to be from pi over 2 to pi. Let me graph that out. Pi over 2 to pi is going to be in quadrant 2. So that means if I was to graph this out, here's my triangle. And if you think about what cosine is, cosine specifically has an x for your angle. Usually it was theta. So that means where this little reference angle is, the little x, or my little angle, is going to be my x that I'm going to put right in the middle. Keep in mind, cosine is let me write this out, SOHCAHTOA. Cosine is the adjacent over the hypotenuse. So from angle x, we're going to use -3 and 5. This is technically a Pythagorean triple. This is a 3, 4, 5 Pythagorean triple. If you didn't remember that, guys, you would have to use the Pythagorean theorem and then solve. Well, good. Now I know what my triangle looks like for angle X. Let's go ahead and look at angle Y. Angle Y looks a little different. So for angle Y, this one is tangent of Y is negative 8 over 15, where 3 pi over 2 is less than Y, which is less than 2 pi. Okay, let me go back over here. I know what the question said. This said from 3 pi over 2 to 2 pi. Here's 2 pi, here's 3 pi over 2. This is where my triangle is. Okay, well, again, this is talking about angle Y. So it said tangent of Y, so I need to put the Y there. And tangent, let me go back to my fraction. This is the opposite over the adjacent. So over here, we're going to make this opposite, which is negative 8, over the adjacent, which is going to be 15. Okay, well, I don't know if this is a Pythagorean triple or not, so we're going to have to use Pythagorean theorem. Negative 8 squared plus 15 squared is going to give me x squared, which is this side. Instead of putting x, let's put w squared, which is your hypotenuse. All right, guys, you guys can simplify it. What are you going to get? W squared, when you simplify it, w is going to give you 17. That's your hypotenuse. Just square those out, multiply it, see what you're going to get. Okay, let's go ahead and finish this up. So over here to the side, let me look and see exactly what it's asking for. It's asking for sine of x and sine of y. Okay, so let me think. Sine x minus y. In the formula, we're going to have sine x cosine y, and I'm just taking this formula from the first page, minus sine y cosine of x. Okay, well, let's think about this. I don't have any real fun numbers to plug in, but I do have my triangles. So when it asks you for sine of x, look at your x. Sine is opposite over hypotenuse. So if you take x opposite over the hypotenuse, you'll be able to create a ratio, which in this case will be 4 over 5. Let's do the same thing for cosine of y. Here's triangle y. We're going to go ahead and do cosine, which is the adjacent over the hypotenuse. So for that next one, we're going to make this 15 over 17. For sine of y, let me look at the same triangle. Sine is opposite over the hypotenuse, so that's going to be negative 8 over 17. And then cosine of x is going to, again, be at the adjacent side over the hypotenuse, which is negative 3 over 5. That was the pre-cal part, guys. The rest of this is algebra 1. We're going to multiply those numerators straight across. 4 times 15 is 60. 5 times 17 is 85. Negative 8 times negative 3 is 24. 17 times 5 is still 85. All we're going to do is subtract. So 60 minus 24 is going to give you 36 over 85. This would be my answer. All right, so we've talked about a lot, guys, and I forgot to highlight my answer here. We've talked about a lot. So the last thing that I want you guys to do, looking at the bottom of the page, I want you to see, is this equation an identity? We talked about verifying and proving identities a while back, but my concern is I could try to, of course, change tangent into like sine over cosine, but this x minus pi is going to freak me out. Okay, let's be honest. If you were solving, I would ask you to find the more complicated side. That's your side that you would want to simplify. So obviously, I hope you guys agree, this will be a more complicated side. What can we do to simplify it? Well, all of the quotient, reciprocal, Pythagorean identities aren't helpful here. I do know something that is helpful, though. This looks an awful lot like this. Only difference is this one is specifically telling you on your page to subtract. So I'll give you a hint. Use this formula, and I want you to try to prove that identity. Is tangent of x minus pi equal to tangent? Prove it. So first thing I'm going to do is I'm going to recopy my formula. We're going to have tangent of alpha minus beta, and that's going to equal, I'm going to put it below, actually rewrite the equal sign down here, equals tangent alpha minus tangent beta all over 1 plus tangent alpha times tangent beta. Okay, so we're going to take that information and we're going to substitute it in. X is your alpha, pi is your beta. So if I was to plug this in, we're going to go ahead and kind of draw my line to show that I'm not solving anything. I'm just kind of making sure both sides are separated. We're going to have tangent of x minus tangent of pi, 1 plus tangent x, tangent pi. Okay, well that sucks. This still isn't equal to tangent of x. Well, let me think. Is there anything I could try to do to simplify? Okay, well let's look at our unit circle. X is completely useless on the unit circle. Completely useless. Tangent of pi, though, isn't. Pi, we zoom in, pi is right here. That's at the coordinate -1, 0. Well, if you think about tangent, as far as your unit circle is concerned, it should be sine over cosine, which is your y over x. So if we do tangent of pi, that would equal y over x, which is 0 over -1. So my question to you guys is, what's 0 divided by 1? That's just going to be 0. It's not going to be undefined. It'll just be 0. So everywhere you see a tangent pi, y'all can replace it with the 0. So we'll have tangent x minus 0 over 1 plus tangent x times 0. That is a 0, not a 6. That should equal tangent x. All right, well, let me get my red pen. The 0 is gone. That's completely useless. Think about this part at the bottom, though. If you multiply tangent x times nothing, you're going to get nothing. So at the bottom, I'm going to write this as tangent x over 1 plus nothing, which is just 1, equal to tangent x. Well, don't make this difficult, guys. Tangent x over 1 is just the same as tangent x, which equals tangent x. Both of them are the same, which means, let me write this over here to the side, this is an identity. This matches up, it's an identity. Guys, the questions that are left in here, I'm not going to do with you. However, these are definitely good problems to do whenever you're studying for your tests and quizzes. So for instance, when you read the composite identities for cosine, sine, and tangent, these are the exact same formulas we just did. So for this one, for instance, for cosine, it splits it into 2 to show you exactly what you're adding and what you're subtracting. And then it gives you the summary, which we kind of looked at on the first page. It also shows you on the next page, sine. It gives you the same thing, gives you 1 positive, 1 negative, and it gives you the combined formulas. And then on the next page, last page, it gives you your tangent, which is the same thing we've talked about. Guys, especially with the sine and cosine, that's technically what we're doing. We're taking the sine, positive or negative, whatever you're adding or subtracting, with the cosine, positive or negative, and we're rewriting it as such, which is this guy here. If I were you guys, I wouldn't try to memorize this part unless you find it useful. This is the exact same formula we saw on the first page. If you have any questions for me, please let me know.